let's restart then. So we will have 2 lectures today because the second lecture was much slower than I thought. So if you want to cover the material in the second tutorial, I need to tell you some more things. So today I want to reach a point where you can understand tomorrow's tutorial in detail. So let me just recall a little bit what we saw yesterday. So yesterday we saw that if we find an R matrix, and R matrix is an object that acts on the product of 2 Hilbert space and gives us 2 Hilbert space, so we represent it as a cross, as an object with 4 indices, 2 incoming, 2 outgoing. And if we find an R matrix which obeys this kind of graphical equation, which we call Yang-Baxter equation, then just as a consequence of this equation, we can show that an object that acts not on a few sides, but on many sides into many sides, an object we can call the transfer matrix. Whatever this object is, if it's constructed by this cartoon, by multiplying L R matrices and constructing thus an object that acts on the full Hilbert space into the full Hilbert space, this object, just as a consequence of R obeying Yang-Baxter, this object commutes with the same object if you use a spectral parameter U and here a spectral parameter V. Okay? So we think of this as having our spin chain, and we have kind of a probe particle with some rapidity U that goes around the spin chain, and the same object, but with another probe particle V. These 2 objects define 2 objects that commute with each other. Okay? Now, this can be, and is, in general, a very complicated non-local operator. It acts on the full Hilbert space into the full Hilbert space. But whatever it is, as a consequence of Yang-Baxter, these objects, for different U's and V's, commute with each other for any U and V. Okay? So what's really crucial, of course, for any U and V. Okay, why is this very relevant? It's very relevant because then it implies that any functional I make out of this T of U, like 1 over T, T plus 2, T squared, exponential of T, log of T, derivative of T, T at 1, whatever functional I do out of this, they will commute with each other. In other words, if I just build things out of T's, I can think of T's as being numbers. So for example, the log derivative of T commutes with the log derivative of T. Just an example. Like T squared would commute with exponential of T, whatever. Now, log of T is kind of a nice quantity, and even more if you take a derivative, but not crucial. Log of T, if you Taylor expand it at small u around u equals 0, you get an expansion where the first term we showed yesterday is nothing but the Hamiltonian, the local Hamiltonian. And if you would compute the second derivative, you would get that the second derivative is a slightly less local charge. It's still a local charge in the sense that it's a sum of an interaction acting any place on the spin chain, but now it doesn't affect only nearest neighbors, but next to nearest neighbor interaction as well. And if you expand further, you have next to nearest neighbor, which is the length for interaction, and so on and so forth. Okay? And why are they local? Well, this was a crucial property of the fact that this is the second important property of the R matrix, that at a particular point 0, that's why we chose to expand it around 0, not around 5 or 7. At around 0, it's given by the permutation. Okay? And because this guaranteed that these objects were local. By the way, at the end of yesterday's lecture, at some point I wrote non-local charges, and it should be local charges. There was a typo in the notes. So I'm underlying here local. They are less local in the sense that the range increases, but they are local. Something non-local would be something like with a double sum, where I would interact here and somewhere here far away as well. This would be non-local. But if something is just interacting in a region, even if the region is increasing in size, this I still call local. Okay? Very good. Now, again, I could expand around 5 and write here u minus 5 and put here q tilde. These q tildes would commute with this object as well. But they would be a bit useless because there would be some monster objects, very non-local and so on. They don't have any reasonable physical implications. That is, in any quantum mechanical system, if you have an Hamiltonian, and Hamiltonian is just a big matrix, I can always find matrices that commute with it. That's not special. So it doesn't mean that all models are integrable, of course. What's important is that the charges that commute with it are local. If they are local, they imply, for example, factorization. They imply that if I scatter 3 magnets, the magnets will factorize. If I tell you that there is some crazy, super complicated non-local charge that commutes with the Hamiltonian, okay, that's useless. That doesn't have any physical content. And now, in particular, because this works for any u. Each charge commutes with any other charge, so all these charges are in involution, and in particular, given that the Hamiltonian is in one of them, the Hamiltonian commutes with all these charges. Therefore, the scattering factorizes, and this implies, it does imply, it's important, I want to emphasize, bit equations. Okay? So we proved bit equations, right? I mean, it's kind of a bit, you might think that there were many steps that we did not do, but actually it's fair to say that we really proved physically, of course not mathematically, a mathematician would not agree with this statement, but we proved this. So let me emphasize again. Why did we prove it? Because in the tutorial, you computed the S matrix. You showed that for two particles, you found what is the S matrix. You found that if the S matrix were any different, the two-particle wave function would not work. So you showed what happened when two particles scatter with each other. We showed that these extra charges exist. So we know that when one particle scatters through many particles, it is just a sequence of scattering events. And therefore, this equation follows. What did we not prove? We did not show that the wave function is what we write even when they are close by and so on. That does not follow from any of these arguments. That would require, indeed, plugging the three-body wave function in the Hamiltonian and checking that we did not need to correct the terms where the magnons are nearby. That we did not prove, right? We don't know what happens when the magnons are nearby. Actually, we know because I told you, but we did not prove it. But for the purpose of finding the spectrum of this spin chain, we did prove it completely. So we really found, I think, the shortest geodesic towards the result by using these physical arguments. Okay, any question about what we have seen so far? Okay, I will not erase that, of course. I never erased the first bar. Okay, so now let's try, let me see, do I want to make any other comments? Yes, I want to just make one small comment, which is that, again, I want to emphasize that, is it a surprise that our Hamiltonian is integrable? And the answer is yes and no. Yes, it is nice that we could find these charges, but we should, again, remind ourselves that if the Hamiltonian is nearest neighbor and has SU2 symmetry, what we wrote was the most general thing, right? So it could be that there are no integrable SU2 Hamiltonians, but if there is one, ours must be the one because there's no another, because there's none other. It's the only Hamiltonian with SU2 symmetry. Okay? So when we drew this diagram with spin chains, integrable spin chains, and then inside integrable spin chains with an R matrix formulation, we could ask, is this space empty or not? If we assume nearest neighbors and SU2 symmetry, there is indeed nothing. This construction is all there is. But if you start now relaxing the conditions of nearest neighbors and going to higher range, you could imagine finding families of integrable models that not necessarily fall into this description. So let's consider an application of this set of ideas. And let's suppose we want to study SON spin chains. So these are spin chains where I have my spin chain. But now at each point of the spin chain, there are L of them. At each point, I have a ket A, where this A takes values from 1 to n. Okay? It's not SU2, just spin up and down. Now it's SON. It's like at each point I have a color, one of n colors, and that's it. Okay? So what could be the Hamiltonian that we could write? The Hamiltonian could be a sum, an Hamiltonian density, n equal 1 up to L. And then what can we write? We can write identity A times identity plus B times permutation. But now there is a new object you can construct if you have SON symmetry that you don't have the right if you have SUN symmetry, which is the trace. So let me be more explicit and write it down, and then it will be clear what these objects are. In terms of indices, this object is delta I1, J1, delta, I2, J2. The indices are just the same. This one swaps them. So delta, I1, J2, delta, I2, J1. And this one is the other contraction. Delta, I1, I2, delta, J1, J2. In pictures, this does nothing. This permutes the two spins, the two excitations. And this annihilates two of them and creates a new two. Okay? So the point is that if we have in SON symmetry, we have the right of using invariant tensors delta with one index up, one index down, or two deltas with two indices up. Whereas this is not an invariant tensor in SUN. In other words, in SUN, we cannot take, say, two spins up and get two spins down. This would violate spin conservation. So this will not be something allowed. You cannot write something. This will not commute with SZ. Right? SZ would measure the spin. Total spin is 1. So you cannot go from up, up to down, down. Okay? But in SON, which is the group of rotations, all these tensors are invariants under rotations. And this is a perfectly valid structure I could write. So there is one more. It's slightly more general. So this is, it's present for SON, but it would be absent if we would want to do SUN. But SON is more interesting because you see that SUN, all you can write is identity and permutation, so we already showed that it's integrable. All we did was not required to SU2. All we did was valid for SUN. If you try to see, as soon as we write it in terms of permutation, we never assumed it was SU2. SUN would work as well, everything we did. So it starts to be interesting because now we really have, it's not obvious that Hamiltonian is integrable. Not everything we write is integrable. You can ask, if I put B equals 5, C equals 7, is this integrable? Or does B and C, do B and C need to be related in a particular way? Now it's very non-trivial. Okay? So in terms of action on, if I act on excitation AB, let's just write it totally explicitly so that everyone understands. Identity gives back AB. Permutation swaps. And this new one, which we call trace, if A, B are the same, it gives all other possibilities. Okay? And why are there three? Yet another way of saying why there should be three tensors, because once you have representations of SON, and you consider the product of two vector representations of SON, right? So you take one vector representation times another vector representation. How do you decompose irreducible representations with two indices of SON? You can have antisymmetric, symmetric traceless, or trace. Right? So these are the three irreducible representations of SON. When you have a product of two vectors, right? Product of two vectors, which is n square, which has n square elements, you can write it as symmetric plus antisymmetric plus symmetric traceless. So this combination is the same as writing alpha times projector into antisymmetric plus beta times projector into symmetric traceless plus gamma times projector into the trace part. We, of course, this acts on site n plus 1. Okay. So this is what we want to understand. This is what we want to study. We want to find what models amongst these SON models could be the nicest of all. Okay? Good. So let's find, so with step 1, let's find an R matrix, R, that could depend on U and V. Okay? Which, again, we write an ansatz for this function. We say, let's say it's A times UV, some function, times So let me put here the indices I, J, K, L. So I could have this times delta Ik delta JL, which would mean this, which would mean permutation. Okay, so you choose whichever you want to write, plus B of UV times delta IL delta JK, which would be the line just go through, which is the same as identity, plus C of U and V times delta IJ delta KL, which would be these two incoming indices they annihilate, and these two create, which would be the trace. Okay? Now this is the most general R I can write. Note in particular that I put here U and V, and I'm not even saying it's function of U minus V. I'm just allowing for the most general possible thing. It's a function of U and V, whatever it is. And in fact, okay, good. That's it. Any question here? Just to be totally explicit, so this is what this R, let's even put the indices, this is R, I, J, K, L. Good. And now we write Young-Baxter. So let's write Young-Baxter. Wow, so much space for the triangle. Let's write Young-Baxter. Let's be very careful. So let's put indices I1, I2, I3 for the incoming indices. Rapidities U, V, and W. Outgoing indices J1, J2, J3. And now we need names for the intermediate indices. Let's call them, say, K, M, and L. And let's put the arrows to see. Okay? So this should be equal to, let's just write it down explicitly. Let me write down. I will write, and then you can tell me if I did a mistake. M, K, J2, J3 of UV. So let's see. This is the first one I wrote. Let's see. Where is this one? So this is this one here, right? So it has incoming indices MK, outgoing indices J2, J3. And the lines, they have rapidities U and V. And then I go on and I write the other ones. Times R. Let's write the other one, the next one, as outgoing indices J1 and M, and incoming indices I1 and L, and rapidities U and W. And the final one, the bottom one, I, which has incoming indices I2, I3, outgoing indices L and K, and rapidities V and W. Okay? And we write that this is equal to a similar thing you can write down corresponding to now the other picture. So this is the kind of equation we have to write. Okay? So I'm not filling in the details corresponding to this, it's clear, right? So again, we put the same U, V, W, the same indices, I1, I2, I3, but now they are scattering in a different order, so we get a different product of our matrices here. Okay?
Right now you're just assuming this and you're going to solve for that.
That's right. So our goal is to find R obeying Young-Baxter. Right? That's our goal. It's to solve Young-Baxter equation. So we write this equation. Now, I'm going to turn on the computer and solve this equation in Mathematica because it's basically very straightforward. All I do is I multiply these Kronecker deltas, I just contract all the indices, and I get a bunch of invariant tensors here, equal to a bunch of invariant tensors there. I compare the coefficient of each of them, tac, 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 and I get a list of equations. Is it clear? But let's see graphically a little bit, get some intuition about the kind of things that are happening because some equations we can get analytically. Let's get one of them analytically and then see that in Mathematica indeed we reproduce it. So one way of saying is the following. One way of getting one of the equations is as follows. So let's draw. I'm drawing a very thin line because I'm going to paint on top of it. So if you have pencil, you might want to do it with a pencil. So let me explain what I'm doing here, drawing this equation. Let me suppose that I choose for the incoming and outgoing indices the following. Let me paint with 3 colors. Let's assume that n is bigger or equal than 3, so there are at least 3 species of particles. And let's color the incoming indices with different colors. So let's suppose the first one is yellow, okay? And yellow starts here, and I want to pick it here. So I want to choose external colors where I1 is yellow and J1 is yellow. So I have to put here yellow, 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 yellow. For the second index, I want to choose orange for the second index here, and orange here. So orange for I2 and orange for J3. Orange for I2, orange for J3. And then I want to choose blue or green. Green is easier to see, right? I want to choose green for I3 and here. Okay? So, and now you will see that I wrote 2 terms equal to 1 term because there are 2 possibilities here on the left for these colors to go from the bottom to the top, but only 1 possibility for the right. So this is the form the equation will take. Let's see on the right. The green line starts here and needs to go here. So as the green line comes, there's no option. The green needs to go straight and just go like this. If the green decides to turn, it's a mistake. It's impossible. So this is the only possible contribution, right? What about the orange? The orange starts here and needs to go there. So the orange needs to turn here and go here. And what about the yellow? The yellow needs to turn here and go here. Okay? So if I consider this process, there was only one way of doing it. Okay? Whereas here, there's more than one way. This orange line can either go like this and go here, or it can decide to do something funnier. It can go left and then turn right and go there. You agree? There were these 2 possibilities. As soon as I specify the path of the green line, the rest is fixed. Of the orange line, the rest is fixed. The rest, the green here needs to go and go here, and then the yellow needs to go here and here, and here the green needs to do this, and then the yellow needs to do the same thing. Okay? So, for example, by choosing these external indices, okay, we get the following equation. So let's see. Here, we have these incoming indices and these outgoing indices. So here we are using the permutation. We are using A. Whereas here, we have the incoming indices and we are using the identity. So here we are using B, and here we are using A again. So you see that in all these pictures, there is one B, which is this, this, and this, and the rest are A's. And C is never used. C is never used because we chose external colors that are all different. So we can never have annihilation of colors producing extra colors. So if you want to find equations that start using C, then you'll start putting 2 green in the bottom or 2 orange in the bottom and so on, and then the colors can start annihilating and producing other colors. But because we chose carefully all different colors, they can never annihilate. Okay? So we have 1B for each of them, and the rest are A's. So I can write this equation in the following way. I can divide the equation. So we write the equation. I'm not going to write. I'm going to write the outcome of the following. Write equation and divide by A of UV times A of UW times A of VW. Because there are always 2 A's, when we do it, we cancel 2 of such factors and we get the following. We get B hat, where this B hat is going to be B we will get B hat of VW, where this B hat is B of VW divided by A of VW. Okay, because the first term would be B times A, but we divide by 3 A's, we cancel 2, and we get the B hat. Plus the second diagram, B hat of the second B is at UV is equal to B hat of the last one, which is UW. Okay. So this is one equation we get, for example. Is it clear? Now, the first comment I want to make at this point before starting to try to solve is that this kind of thing, solving for a ratio, is perfectly reasonable, and it's what we should expect. Because, of course, Young-Baxter will never fix the overall normalization, because I can always multiply my R matrix by an arbitrary function of U and V, and that function will just factorize in the equation. Okay? So this is what it should be. So this makes sense, and indeed, we can set, if we want, A of UV equal 1 without any loss of generality, because the overall normalization is irrelevant for Young-Baxter. If I multiply by a general function, that function will cancel out on both sides of the equation. Good. Now, what is the solution to this equation? This tells you, see, this only depends on U and W. And this, right, left-hand side, depends on V. Right, so what is the solution to this equation? The solution is more obvious if we swap these 2 terms. At least for me, I don't know. For other people, it might be the same. Imagine swapping the 2 terms and see if the answer comes to your mind. Sorry? Someone said something? No? So what's the general solution to this equation? Sorry? So someone said U minus V. Let's see if U minus V works. Here I get U minus W. And here I get U minus V plus V minus W. Indeed, the V cancels and we get U minus W. Right? It works. But it's not the only solution. You see this cancellation, any function of U minus the same function of V would do. Okay? Because you just plug in time. However, we did not define what is U yet. U is just some arbitrary complex parameter. So we write it like this, but right away we say that this is our new U. Let's call this U. If you want, we start with U tildes, and now we call this U, starting from now. So without loss of generality, we can set A of U and V equal 1, B of U and V equal U minus V. Okay? Yes.
Is it possible that if A vanishes somewhere so that you can't necessarily divide it out, there could be some solutions where it sort of holds almost everywhere except some bad points or something like that?
Yeah, of course, those kind of things could happen.
So then this isn't quite everything.
Yeah. That's good. We could imagine having some very exotic solutions of Young-Baxter where A will vanish. Then we can, after finishing this, we can go and say, let's assume A is 0 and try to see if we missed any solution. We did not, but we could have wondered about that. Okay, so this is where we stand. Okay, and now we start to sweat a little bit because we already fixed 2 functions and we have many, many more equations. And now we could imagine perhaps now we start choosing different colors and things would just not work. Because in general, we have many more equations than functions. So now we can start being nervous. Okay, now I will choose different colors. I will swap in my picture the green and the orange. And I will find some equation that will be inconsistent. Okay? And indeed, Young-Baxter is very, very constraining. And now we have to suffer a little bit. We could now choose different colors and start seeing, but now I'll go to Mathematica and do it all automatically, which amounts to picking all possible colors, and we will see if it works or not. Okay? So the idea now is plug this into Young-Baxter and see if we can fix C of UV, or if we get an inconsistency right away. Okay? Okay, perhaps let's do the following to make it optimal. Let's do this part of plugging in Mathematica after finishing the explanation. Let me tell you what the solution to this is, and then we'll go and plug it in Mathematica. Okay? So conceptually, it's more or less clear what we are going to do, right? Very clear. So the outcome of doing this is that it's possible to find C, and C of UV is equal to minus 2 times U minus V over 2 U minus V plus N minus 2. Or, there are 2 solutions, C of UV equals 0. Okay? And this is nice, because what is this solution with C equals 0? Well, this solution better be there, because this is nothing but the SUN solution. This is nothing but saying that, in particular, if we have an SUN R matrix, it obeys Young-Baxter. So there is a solution to Young-Baxter where we don't put a trace, which will be a forbidden tensor in SUN. So this is telling us that there is a solution when C is equal to 0, which is just identity plus permutator. And you see that this solution gives an R matrix, which is just U times identity plus permutation, which is what we had in yesterday's lecture. Up to an I, but that's just redefining U. Doesn't matter when you put U to 0. Okay? So we put V equals 0 in yesterday's lecture. Otherwise, R of UV would be U minus V times identity plus the permutation. Okay? Because there will be just B and A. Okay? So this is the R for SUN. Okay? So now we really finished this proof. Okay? I lied a little bit. There was one more step missing. I have to show you that our matrix obeys Young-Baxter, which we did now. Okay? Now we know our matrix obeys Young-Baxter. We justify everything we did. So now it really closes the loop of ideas we had before. But we want to go on and comment a little bit now on this solution. This solution is different. So for this solution, then it means that R of U, let me just put U. So I put 0 here and U here, is equal to U times identity plus permutation minus 2U divided by 2U plus N minus 2 times trace. And this means that if I construct an Hamiltonian in the usual way, namely by taking ddu of log t at u equals 0, okay? First note something nice at u equals 0. Our matrix of 0 is equal to permutation. So that's great news, because this was something nice that was guaranteeing that the Hamiltonian was local. If we put u equals 0, the coefficient of the identity and of the trace both vanish. Okay, so that's nice. That's good. And what do we get? Well, the same story as before. If we repeat the same analysis, just taking the derivative, we would get that this Hamiltonian is equal, so the Hamiltonians that are integrable would be equal to a sum of something times identity. This we can never fix. This is just an overall shift of the energy, as I said. And in this language, you can see that if you multiply the R matrix by any function of u, this just shifts its log derivative by a constant. So that is unfixable, which makes sense. Who cares about the zero of the energy? Plus some constant times, if we put some constant here, of course, some constant times a none. What matters is that we get permutation, and the relative coefficient would be between permutation and trace, if you repeat the same analysis, would be that you would read off from there, minus 2 over n minus 2 times trace. Okay? So here is what we conclude. We conclude that if you prepare in your lab an Hamiltonian with SON symmetry, you better choose your material such that the coefficient of permutation and trace, they should be related by this relative coefficient. Okay? So for example, let's suppose I take an SO6 spin chain. Then an Hamiltonian, which would be sum of identity minus permutation plus k over 2 would be awesome. I'll put a smile here. But if someone would give me an Hamiltonian with a minus here, it would be terrible. Okay? So immediately you see that there are some Hamiltonians. So if I write down these two Hamiltonians with plus and minus, right? And now I will start putting some particles and I will scatter them against each other. And you see, without any computation, I can tell you. If you choose the plus sign, you will see something very nice. You will scatter 3 particles and they will just factorize. If you choose the minus sign, okay, I wish you good luck. Because then, okay, you'll scatter 3 particles and get a mass compatible with energy and momentum conservation, but a priori, no reason for any conservation, not even conservation of number of particles, nothing. You will just get whatever you will get, and you will have no control. Then your only hope is take this Hamiltonian, put this 6 to the L times 6 to the L matrix, because it's the dimension of the Hilbert space in a computer. And okay, if it's 6 to the L by 6 to the L, maybe you can solve a spin chain of length 6, and okay. And that's it. And you stop there. However, if the sign is different, then awesome. Then we can write down some bit equations and just solve it for length 200, length 1 million, whatever length we want. And use by solving some simple algebraic equations. Okay? Good. Now, so this is an application. As you see, this method is quite powerful. You could imagine now doing other groups, trying to see if we missed some more esoteric solutions, like, what's your name, sorry? Dylan, like Dylan was saying. Can it be that there are solutions where we cannot set A to 1? And now people, indeed, they explore solutions of Young-Baxter. There are people working in integrability trying to understand what are all integrable models, trying to see if there are some exotic solutions. Say, here we found that this B of uv was a function of u minus a function of v, which is equivalent to saying it's u minus v. But do all integrable models need to have our matrices of difference form, which are just u minus v, or could there be something more exotic? And there are some models which are more exotic, but very rare. For example, you might have heard of the Hubbard model, which are models that describe electrons that move on a lattice, just electrons on a lattice. That model, for example, is integrable, but the underlying R matrix is not of difference form. But that's more or less the only example people know, for example. So, yeah.
I mean, it's just a comment about the general procedure before we get to those coefficients. Like, if I looked at that there and I already knew about the SUN spin chain, then
You already knew about
the SUN spin chain, that it was an integrable spin chain. And I, for instance, knew that A and B had to be whatever the values were for the SUN spin chain. Then I know that C equals 0, there has to be some case which is still consistent, and I know those. So is there some way in which I could just add this new invariant operator and then ask, or the tensor, and then ask, find the right sequence of these guys to just find that coefficient through this, or would that miss too many?
That's right, that's right. So let me rephrase so that everyone understands. So, what's your name, sorry? What Vasilev is pointing out is that if we have this set of equations, we know that we can choose external colors where we will not probe C, right? So by choosing these external colors, like I did, we will get the same equations that we got for SUN. So A and B need to be the same as they are for SUN, right? So there's no freedom. So A and B, they have to be this U times identity plus permutation, because this was the solution for SUN. But we did not prove it yet, so I could not use it. So if we had derived it last lecture, I could use it and could start directly by fixing C. I chose instead to first derive B, and then, of course, we could fix C. Now, if we knew already what happens when all colors are different, then indeed, what I should do is start here and pick a picture where two colors are the same, which will be a picture that will pick out C once I know already the other A and B, and this would be the way to fix it. That's in practice what we are going to do now, but we are going to do it in Mathematica. So finally, let me just make a comment about the connection, about the difference, conceptual and mathematical difference between this object, which is the S matrix, and this object there, which is the R matrix. Okay? Okay, so the first obvious comment is that R matrix is not equal to the S matrix. It's not the same thing at all. Okay? For example, for the XXX spin chain, the R matrix is a 4 times 4 matrix. It's a 4 times 4 matrix that which is identity plus permutation, whereas the S matrix is a number. It's not even a matrix in this case. And it is just, in this case, U minus V minus I over U minus V plus I. Okay? So they are not the same thing. Yet, they obey the same graphical, they have the same graphical picture we said. Okay? So both obey that if I multiply them in this order, that we get the same thing. Now, in this case, it's non-trivial. In this case, it is just the fact that if you multiply numbers, you don't care. Right? You multiply ABC, it's the same as CBA. So of course, once it is a number, it obeys this equation. It's just numbers commute. There is literally nothing to check. But now we could imagine a model okay? So this would be an SU2 spin chain. So now let's suppose we would consider an SU3 spin chain. So for SU3 spin chain, we would say that we have our vacuum, which can be 0, and then the excitations can be 1, or they can be a 2. Okay, so now it's a three-dimensional Hilbert space. So we have two kinds of excitation, ones and two, not just spin down on the vacuum of spin up. Okay, slightly more complicated. Now, what is the R matrix? R matrix is the same as we said. It's U times identity plus permutation. But now, it's what's the size? If I want to write as a matrix, what's the size of this matrix? Is it clear why it's 4 by 4? It's just that it has. Is it clear why this matrix is 4 by 4? Because this matrix here, if I put it as a matrix, I have up, 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 down, down, up, down, down. Right? These are all the incoming states, and these are all the outgoing states. Right? So what about for SU3? What would be the size of that matrix? 9, right? So we have all possible AB, where A runs from 0, 1, 2, right? And B as well. So this would be a 9 times 9 matrix. Which obeys this equation. But what about the S matrix? Now it's kind of interesting. What about the S matrix? Well, now the S matrix is not a number. Things are more complicated because when I scatter, I can scatter 2 1s, or I can scatter 2 2s, or I can scatter a 1 against a 2. So now the S matrix itself is a matrix. Now the S matrix is itself a matrix that takes an index AB into an A prime, B prime, where A is 1 or 2 and B is 1 or 2. Right? This is the most general thing. So now this S matrix, right? This S matrix itself as a matrix, because the theory is integrable, because we constructed it out of an R matrix, should obey Young-Baxter. So this is a 4 times 4 matrix with a rotation symmetry between U and 2. So with an SU2 symmetry, okay? With SU, let me write 2 as 3 minus 1, because you see that if it was SUN, it would be SUN minus 1. With SU 3 minus 1 symmetry. So this S matrix, which obeys, again, Young-Baxter, now both the R matrix and the S matrix are non-trivial, and this S matrix here, S of UV, would be now fixed by Young-Baxter to be proportional to U minus V times identity plus permutation with some function f of UV that I would have to fix. I can put an I here if I want. Which is, of course, where this is nothing but the R matrix of SU2. Okay? Where this would be the R matrix of SU3. Okay? And we could even fix this function f, because we know that if we restrict one SU2 subspace, we know what the S matrix gives. So I know that if I scatter 2 particles with index 1, right? If I scatter 2 1s, I just get 2 1s back, and I know what the phase should be. Should be this U minus V minus I over U minus V plus I. So let me put here a minus I. So I know that if I put 2 indices to be the same, I know what it should be. So I actually know this should be 1 over U minus V plus I to get the correct 1, 1, 1, 1 scattering, which is the SU2 subspace inside the SU3. Right? When I put 2 1s, identity and permutation both give 1, and then I could even fix this F. So you see, without any computation, we could fix the F of an SU3 spin chain. And more general, you see that the F of an SUN spin chain is proportional to the R matrix of an SUN minus 1 spin chain. Okay? So the R matrix is kind of, I mean, physically, the R matrix is kind of related to the UV of the theory, saying it's kind of a microscopic ingredient out of which you construct your spin chain, something out of which you take log derivatives and you start building your spin chain. It's the nature of space-time, if you want. It's about constructing your spin chain out of these R's. It's what gives the locality and so on and so forth. Whereas is related to the opposite. It's related to the infrared property of my theory. If I take two faraway magnons and scatter them, what are the possible outcomes? Okay? Mathematically, they are, of course, related. And in particular, when you have S matrices of a given theory, what typically happens is that the S matrix is proportional to an R matrix, because both obey the same equation, but the concept of proportionality is not always as simple as here. So you could imagine having some quantum field theory, which is integrable, not a spin chain, or some complicated, more complicated non-local theory, which is integrable. Then, from the point of view of the matrix structure, you know that the matrix structure has to obey Yang-Baxter, so then it must be proportional to some spin chain R matrix. But the overall coefficient, the overall magnitude of the scattering process, it could be much more complicated than this simple rational stuff. This is what happens in the real life. Okay? Good. In other words, what we have here is the symmetry of the spin chain, SU3, and what we have here is the symmetry of the excitations, of the particles. Right? The particles, they don't have SU3 symmetry. The particles, you can rotate a 1 into a 2 into a 1, and so on. Like there, particles have no symmetry at all. Particles are just excitations that I put on my spin chain. There's nothing to rotate them into. I just put them there and they move. But here, no. I put a 1 or a 2 and they form a doublet of SU2 and I can rotate them amongst themselves. Nothing distinguishes a 1 from a 2. It's the same thing. So you should always have in mind when you have a spin chain system, you can imagine doing an even faster geodesic towards the result. You might imagine having a complicated spin chain, and then you can ask, okay, let me first find the R matrix. After finding the R matrix, I find that the theory is integrable. Once I find that the theory is integrable, I make an ansatz with two particles. When I make an ansatz with two particles, I solve it. Then I find the S matrix. Then I plug the S matrix in bit equations. And then I get the spectrum. That's good. But you could be even faster. You could just say, I have my spin chain. I don't care about the symmetry of the spin chain. I will ask what's the symmetry of the particles. I will go and draw a particle and say, what's the symmetry under which they transform? And immediately, by knowing the symmetry under which they transform, I will write directly what's their S matrix. And I will forget about Hamiltonian and everything. I'll just go directly to the object of interest, which is the S matrix. And once I know the S matrix, I can write bit equations. So this concludes the philosophical part. And I would like now to fill in the gap and to show you how to do this kind of manipulations in Mathematica. Not because the manipulations are particularly useful in this case. I think conceptually it's clear. But because I think everyone should know how to manipulate delta functions and Kronecker delta and tensors in Mathematica. It's kind of something important to know. So that's what we're going to do now. Any question?
So what do you need to assume that the vacuum is a product state?
I need to know what are the symmetry of my excitations. Okay, no. The answer is no. So let me give you an example where it's definitely not a product state. Okay, but it's kind of a complicated example. I mean, perhaps, I'm not sure if this will confuse people, but okay, let's try. So what happened here was that we decided to, I think I took the wrong adapter. Does someone have a Mac adapter? What's this? Sorry, 1 second. Okay, I need a Mac adapter, please. Or a way to plug this into here. Okay, so then it's good that I have a question. So here what happened was that we are studying ferromagnetic vacuum. Ferromagnetic vacuum is product state as, what's your name, sir? Anthony is saying, you have a product of spins up, so you have up, and that's it. And you break the symmetry. You add SU2 symmetry, and you chose a vector pointing out, and you broke the symmetry. So you broke the symmetry completely, and now instead of having SUN symmetry, because you chose one direction for your ferromagnetic vacuum, now you have the remaining SUN minus 1 symmetry. Okay? And therefore, particles transform under SUN minus 1 symmetry. But let's suppose we want to do something funnier, and we want to describe the antiferromagnetic vacuum. The antiferromagnetic vacuum is a very complicated state. You might think, oh, it's very simple, just up, down, up, down, up, down. It's not. It's a big, massive linear combination of many, many terms which form a big singlet, and it's a complicated state. It's not at all product form. It's a state that is a singlet. It doesn't break, thank you. It doesn't break any symmetry. So now it's a state that preserves SU2 symmetry, contrary to my ferromagnetic vacuum that breaks SU2 symmetry. So now, suppose I'm going to take my antiferromagnetic state, which doesn't break any symmetry, and I'm going to put excitations there. Okay? Now you have to ask, what are the excitations around the antiferromagnetic state? It's more complicated now, because the state is so much harder to describe that we have to reanalyze what could be the excitation. So if excitations around ferromagnetic are called magnons, those ones are called spinons. So it's a different kind of excitation. And these are different excitations. Maybe I will describe them a little bit in my lectures, maybe not, I don't know. We will see. But these spinons, they are excitations that now they don't break, they are on a vacuum that doesn't break any symmetry. So these excitations, they are SU2, they transform under the fundamental of SU2, they are spin 1/2 excitations, and they can be up or down. They can be whatever. It's not like the magnons that don't have degrees of freedom, that are just spin down and that's it. The spinons, they preserve the symmetry. So what you know is that if you take the antiferromagnetic spin chain and consider the scattering matrix of spinons, the scattering matrix of spinons is proportional to the R matrix of SU2. So for the SUN spin chain, if I want to study spinons, then the R matrix and the S matrix, they do coincide exactly. It's not like one is the other one with rank -1. And that's because there is this vacuum which doesn't break any symmetry, which is a singlet vacuum. So we know that this vacuum, okay, here it's really a physical proof because there are several gaps there. But I could argue that if there is this, this singlet vacuum, and if I put their excitations, because the underlying theory is integrable, these excitations should be integrable, but they preserve a given symmetry, and therefore they should factorize, and given that they have SU2 symmetry, they should be proportional to the R matrix of SU2. Another way of doing it, of trying to reach this conclusion, is trying to see, okay, given that I can describe the ferromagnetic vacuum very well, here is the full description. Let's start with this description around ferromagnetic and go to the antiferromagnetic, which is a very excited state. So you start from ferromagnetic, you put 1 magnon, 2 magnons, 3 magnons, until you put n over 2 magnons. It's very, very far away. And then it's like filling some Fermi sea. Now you will describe some effective description around that state. And you go, you describe it, and you see that those equations, they have an effective description in terms of equations where you get these particles where you restore this symmetry and where the S matrix is the R matrix of SU2. So the answer is no, you don't need to assume that the vacuum is factorized. However, if from the beginning you have to start with a vacuum that is not factorized, it's very hard. So I don't know how to write the wave function of the spinons, for example. That's very hard. But I don't care. If I want to describe the bit equations of the spinons, what's the periodicity conditions for the spinons, what's the excitations around the antiferromagnetic, I don't care about that. I fix the S matrix using symmetry and by starting with this ferromagnetic and going up to there. And then I describe some effective bit equations, which are perfectly fine. So what often happens is that you have a very simple state around which everything is very easy to describe, like ferromagnetic. And in integrable theories, you can even reach the other complicated states, but some things you don't want to do. You don't want to see what happens to the wave function, for example, because that's just too hard. The spinons are non-local objects, it's complicated.
So in this construction, does the locality of the excitation matters? It seems to me it's very important. If if like here the excitation is just locally on one side.
Yes.
But if it's a spin-on, it may extend over the range. So would that change our condition? Like we need to at least contain some next nearest neighbor or
Good. So what happens is that in general, if you have a theory where the interactions are non-local, these equations are not exact. There are corrections to it. For example, suppose we have a quantum field theory. Okay, so we have particles moving on a line which is continuum, and they scatter with each other by exchanging massive particles. For example, suppose a theory that just has massive particles. What would be the correction to bit equations? Well, in that case, we would have a picture. So let's consider a quantum field theory. We scatter a particle and it goes all around. And this will be equal to 1. But that's not exactly true because, as you are saying, these particles are a bit delocalized. And they start filling the range of this excitation. So there are corrections, which in that case would be, for example, exponentially suppressed with the mass of the lightest excitation, for example. And I would have to worry, if the length is not so big, do I start to have these so-called wrapping corrections where the excitations go around the world, and I will have to understand how to take them also into account. So if the spin chain is very large, you typically don't worry. As soon as you start considering smaller and smaller and smaller spin chains, sometimes you start worrying about finite size effects. Here we don't because it's nearest neighbor. For the spinons, if you consider spinons for a very, very big spin chain, you also don't care because they have some finite size and there is enough space in the spin chain to make sure they are all well separated. But if you take spinons on a very small spin chain, then you start asking about finite size corrections to the effective Witten-Zatz description of the spinon. I mean, it's kind of an advanced question. Perhaps, I'm afraid that people that are not so familiar with spinons and so on might be getting a bit lost. But perhaps you can ask me more in the break. Did I answer your question more or less?
Yeah.
Very good. Okay, so good. So I'm sorry we will go a bit over time, but I don't want to start with mathematics in the afternoon. But it's going to be fast. This is very simple. Okay, so what we want to know, to implement, is the equation for the R matrix that is hidden there. Okay? So the first thing I think is quite convenient often to do is the following. We will have some R matrix R with arguments U and V, and incoming indices I and J, and outgoing indices K and L. And you see it's already becoming a bit hard to read even for a single R matrix. Okay? So if I start defining this object, it's already starting to be a bit tough to work with because it's already, too many brackets and so on. So something quite convenient that I encourage people to do is in the beginning to load some notation. Okay? Let me quit my kernel. So I load some notation. Then I click here, and I say that instead of using this crappy notation, let this be equivalent to putting some index I, J down and some index K, L up. Okay? This just allows Mathematica that when I write the stuff on the left-hand side, she recognizes as the thing on the left. On the right, on the left, they become equivalent. And if I have, for example, a delta function, we also like delta ij to have indices down, right? So we want this to be equivalent to delta ij. Okay? So this is just convenient. So now if I write delta ij and ask Mathematica, what is this? She will say it's delta of ij, right? Whereas if I write epsilon ij and ask Mathematica, what is this? She will say it's superscript of epsilon with arguments I and j. So in the first case, she's recognizing the syntax as being the original one. Okay, very good. So now, even if I take this, now I can ask Mathematica to make it nice, and immediately she brings it to the reasonable form. And we say it's A of uv times delta, and now we start writing what we wrote, delta ik, delta jl, plus b times I swap k and l, plus the trace, plus c, delta ij, delta kl. Well, KL and LK doesn't matter. So we say that, let's say that delta is orderless. So the arguments of delta don't matter. So when I write delta Ji minus delta Ij, automatically it's 0. Okay? Good. So now we defined our R matrix. And now we write our matrix with Km, J1, J2, view V times a bunch of our matrices, ta ta ta. Let me see if I have it open so that I copy, otherwise it's a pain. Okay. So this I'm going to spare you the pain of writing it down. So this is just a product of our matrices now. Okay? So you see, we multiply 3 R matrices equal to a product of 3 R matrices. What should I do now? Open up these parentheses, get 27 terms equal 27 terms, contract the delta function, so delta KL times delta KM, this gives delta LM, and so on. Then I will get 15 delta functions equal to 15 delta functions. I think is it 15? Yeah, 15 invariant tensors equals 15 invariant tensors. So we'll get 15 terms equal 15 terms. It will give me 15 equations. And then I have to solve those equations. 15 or less, at least at most 15. Okay, so this is what we want to do. So now let's try to do that. So we expand. And now we need to, all these terms, each of them, we want to simplify these Kronecker deltas. Okay? So what do we do? Well, we say, if we have delta AB times delta BC, replace this by delta AC. Okay? And we say, do this until you are tired, which means / dot, until you cannot do anymore. And this is done, except that we have some delta squares here. What is delta square? Delta Mn squared is delta Mn times delta Mn, which is delta LL, which is N. So we also do replace delta, if you have the same thing square, this is just N, the number of colors. Then we do it, and this is what we get. Huh? Ah, no, AB squared, sorry. Good. And this is what we get, right? So now this must be equal. So what we do is we collect. And now, you see what I did? I just collected in delta. And I say this must be 0. The next one must be 0. The next one must be 0. This one must be 0. All coefficients of deltas must be 0. So I put an F to capture, and all these arguments of F must be 0. Okay, and now I find all arguments of F. All of them, so I put them in infinity, so that she looks very well. And this gives me, let's call these equations. So this gives me a set of all equations, you see, a bunch of equations. This should be 0, this should be 0, this should be 0, and so on and so forth. Okay? So how many equations? 1, 2, 3, 4, 5, 6, 7, 8. 8 equations we have to solve. Okay? We could get up to 15, but some were automatically 0. Okay, good. Now we take these equations and say where A of U of V, let's set it to 1, because we agreed we could do it. Okay? So you see here in the next to the last line and also above, here is our equation that we derived analytically. B of UW equal B UV plus B VW. You see, Mathematica wrote it in a way that is smarter than I did. And B UW, the same thing. So these equations are the same. In fact, we could ask to remove the duplicates in the beginning. We could have simplified a bit, but it doesn't matter. So now we know also what we should do. We should replace, we had agreed before that we should also replace B of UV by U minus V. Okay? So now 2 equations are automatically true. And then we get the other ones. We get a bunch of equations for the remaining ones that we now solve And we solve the other equations for CUV, CVW, and CUW. Okay. And we full simplify. And yes, nicely, it did work. It gave us, as I said, as I told you, either C equal to 0, the first line, or CUV equal U minus V over U minus V plus N minus 2. Okay? So this is the one I said. Of course, something could have happened when I did this. It could have here plus W. Then I knew that this is nonsense. Of course, then I would just say it would mean that there is no solution. Okay, very good. And what we are interested is in the last solution. So we take the last one. And this is our solution for C. Okay? And now we can just take R, I, J, K, L of UV. Replace this, and replace C. And this is the R matrix that, that we derived, that I told you we would get as function of U and V. Okay, I told you it was going to be fast. Okay, so let's re-meet again at 4. Any question? So now, let me just say what we are going to do. We are done with this understanding of integrable models. Now this is really rigorously derived. Now what we are going to do is explore the physics of this spin chain. So now for a few lectures, we are going to be basically playing with these bit equations and seeing what physics can we extract, what can we learn about this, this magnetic model, what is the underlying physics, and we are going to make contact, as we said, with field theory, as I had promised at some point, and this is the direction where we are headed. So now we are going more into the physics of this material.